hope it doesn't fall off. Good morning, everyone. I'm very happy to be here. Thanks so much for inviting me here, and I'm happy to see a lot of people in the audience, and I hope some of the things that we've been doing make sense. And even though so this is part of ongoing work that we've been working on since several years now, towards the end of my postdoc as well as my last year at IIT Kanpur. So I'll give you a flavor for what we are doing, why that is relevant, why that's meaningful for me, and I'm happy to address questions at the end of it. Even though I presented this a few times earlier, like each time I am talking about this or I'm on stage and I'm looking at people, I tend to start feeling goosebumps, and my heart is racing, and I feel like maybe I should just run away. But sometimes it also helps to sort of look at people, calm down, speak about the daily activities, and try and get things back in control. But it might not be the same for all of us, and it might not be the same for all of us at all times, right? That is really what anxiety disorders are all about. So I will start with what we know about anxiety disorders and the gaps that we have today in the healthcare system, and then I'll move on to talk about a different approach that we're using to really understand anxiety and hopefully come up with a better way of keeping things under control. So what is anxiety disorder? So here I'm going to talk about a specific condition called generalized anxiety disorder. As per the Diagnostic and Statistical Manual called the DSM-5, the latest of which talks about anxiety disorders as excessive anxiety and worry. That is, you tend to think a lot about certain things that are not under your control, and you are basically not able to get those things under control, which is sort of like a negative feedback and continues to increase your anxiety level. And you find it very difficult to control those worrying tendencies. And there are a lot of other side effects of this, which is you tend to be very irritable, you tend to be very fatigued because you're thinking about all this, and it is very draining over a period of time. And all of this put together, and if it's there for a period of time, you tend to be screened for an evaluation to diagnose you with a condition like anxiety disorder. And this is like, if I say show of hands, how many of you feel anxious? I mean, a lot of us feel anxious at all times, but some of us might get diagnosed with anxiety disorders, and there are about 600 million people worldwide who have been like either diagnosed with anxiety or depression. And it seems to be the highest in the age group of 20 to 40, which is sort of where a lot of us belong. And twice as much and the incidence is twice as much in women compared to men. So it is a very highly prevalent condition, very insidious. Like, it seems like it has the qualities to reduce the quality of life for us, and there is something that we need to do as quickly as we can to improve the quality of life in some sense. How do we currently go about this? It is a very trial and error approach. You go to a physician and they give you a certain drug, and you wait and see whether that works or not, and then you go back again if it doesn't work, right? The problem is that we lack an objective measure. We don't have, like, what would be really nice is to have something like a thermometer that says this is your anxiety level and this is how it is changing over time. But unfortunately, we all depend on self-reports, and what is being diagnosed is based on a set of symptoms. And the neural basis for all this, like if you, let's say, understood where in the brain what is happening, and if that particular thing can be tweaked, that would be amazing, but we still lack any such understanding of the condition. So, yeah, as I said, it would be really nice to have something like an anxiety thermometer that gives you a readout and also tells you how you're improving based on a particular therapy or condition. So essentially what we're looking at is ways to shorten the time to recovery by having better diagnostics and better objective measures for the condition itself. So that's really where, like, we are starting to think of it in a certain way. To go back in the developmental timeline, so what really leads to anxiety disorder? So this has been something that people have been thinking a lot, and there are certain ideas out there which are very prevalent. For example, a very powerful hypothesis states that we have some genetic predisposition. So let's say there might be some genetic predisposition combined with a lot of environmental stresses. Like in early life, followed by later life stress. I mean, life is stressful, and then like of course some people experience more stress than others, and maybe this genetic predisposition combined with continual onslaught of stress puts you on the path for anxiety disorder. So you might see someone diagnosed with trait anxiety, that is, you tend to worry a lot, have excessive worries, and those are not under control. When it actually can move on to become full-blown anxiety disorder later in life. So people have been trying to understand. I think those were the pointer was, but trying to understand how it could the environmental factors and biological predisposition will put you in the trait anxious situation, which converts into anxiety disorder. The question is whether you can catch this, looking at how people are making decisions. Okay, this is better. Okay. Okay. So you want to catch, and of course, anxiety influences how you make decisions, right? Like I might be like very anxious, and I'm not remembering the lines that I prepared to say, and I go back and forth, use some words again and again, and that is the kind. I mean, that is how it interferes with how you make decisions on a daily basis. And the idea here really is that if we can use the way we make decisions, the circuits that underlie that, by using powerful computational models and with neural signals, can we get a better grip over what is going on? People have used this in the past. It's not like that's not been done before. There is a particular task called the dot probe test, which is very easy to explain. So where all that you have to do is judge whether these two dots are horizontally oriented or sometimes they are vertically oriented. But before you judge that, you're made to see certain faces on the screen. And these faces can be neutral, or sometimes they can be highly emotional. And when they tend to be highly emotional, people are attracted or captivated by those images in such a way that it takes them longer to report the orientation. This is called an emotional capture task, and people have used this successfully to understand how someone is anxious because they tend to be more attracted to these or more captivated by these anxious looking faces. Although this has been great, there have been issues with the task. It hasn't really scaled up, and there have been inconsistent results, which really brings us to where we are right now. Can we come up with a better measure for how anxiety impacts decision making? So here I'll make a little segue into explaining what is fast foraging, and you all probably have experienced this in one way or the other, and how this is a neurophysiologically relevant approach and why this makes sense at all. So what do I mean by fast foraging? This is the simple art of going about picking or collecting food. If you've gone to the orchard and tried to collect fruit, you've pretty much engaged in the kind of fast foraging that I've talked about. So fruits are on trees, and trees are not everywhere. They're there in like one place or the other, and you could climb up one tree and collect fruits for some time, and then you realize that okay, I think my time is worth. I mean, it's probably not as much. It's not worth spending more time in this tree, and I might as well climb down and walk to the other tree, right? So you have to come to a conclusion at some point and decide that you might as well go to the next tree, even if it costs you some energy and time where you won't get any fruit. So that is really what fast foraging is about, and we all do this very naturally because we have to fend for ourselves. Like in city life now, we can get access to food through blinkets, but most of our evolutionary life we've actually spent getting our own food, and animals have done this, still continue to do this. And this is a behavior that's conserved across species. So you can see this. I mean, getting food is one of the most innate behaviors across species. And in fact, there is a very strong candidate hypothesis that says that the primate brain size, so if you go from lemurs to gibbons to chimpanzees to humans, that primate brain size is in fact directly correlated with the complexity of their foraging habits. So if you have to like go up the trees, look at the color of fruit, and ward off other animals to get access to those fruits, then that requires a lot of calculated planning and strategic decision making. That in fact, eventually, maybe that's why your brain size is larger. And it also provides a normative framework. What do I mean by a normative framework? As I just said, you have to keep track of the rewards that you're getting and decide at some point that the reward that I'm getting is not worth the time that I'm investing in this particular tree. And it is still worth spending that much time with no fruits, even if I have to walk to the other tree, right? So you have to compare, evaluate reward, calculate the trade-off in terms of energy and time, and make those decisions. And it might sound very complicated, but we do it naturally. We are not thinking in terms of all this and putting numbers into a calculator when we are actually thinking through, right? But I will show you how that we are naturally evolved to solve these problems in a very optimal way. But it provides a normative framework because now if you see that somebody is doing this very suboptimally, if they're on one tree and they're not just leaving that tree, or if they continue to go from one tree to the other, after taking one fruit, all of this is suboptimal, right? At the end of the day, they're going to get less fruits than the other people. And over the years, we've also started to understand where in the brain all these complications are happening. So we know, for example, there are regions in the brain where reward and time cost that I talked about are being compared, calculated, and balanced out. And you can put electrodes there and really read out these signals to understand how these calculations are evolving over time and what changes under certain conditions. And the anterior cingulate region, so this is the brain sort of cut into half when you're seeing from the sideways, you're looking at the brain, and there is a particular region called the anterior cingulate, and that is the region I was referring to when I said that the cost reward balances are being computed over there. But what is interesting is that these same regions are also implicated in anxiety disorders. So that's why we sort of use this idea that if there is something happening, if there is an anxious person doing these calculations, it has to be already pre-activated, or there has to be some kind of an influence of their state bearing on their activity at that point in time. And lastly, one more conceptual slide that you might think, what does anxiety have to do with all this? But if you think of the situation where you are disengaged from a patch, or disengaged from a particular tree that you're in, this could perhaps be thought of in some ways as being similar to disengaging from thoughts. And this happens all the time when you're anxious, right? Like you're trying to stick and focus on something that you want to work on, but maybe you left the door open, maybe there's something on the stove, or maybe there's something else that you forgot. This is essentially disengaging from the present. That is drawing you out of what you're trying to do at the moment. And maybe fast foraging can latch onto that circuit and tell you exactly how that circuit is being impacted. So what we did was to make a virtual fast foraging task. So this is, of course, we can't take people to the orchard, so we brought the orchard to the lab, right? So we made a game where people have to collect fruits, and it was made as simple as possible so that we could keep track of a lot of things that were going on. So the task looked something like this. So they would go to a particular patch here, and they would collect fruits, and each time you collect fruits, you get fewer and fewer fruits, kind of resembling what happens in real life, right? Like you get more good fruits at the beginning, low-hanging fruits at the beginning, then it gets harder and harder. You have to either go up or you get less poorer draw of the lot. And at some point you can decide that it's not worth staying there. At that point you press the other box, and that allows you to travel to the next path. So this is one of the most simple renditions of like a real-life fast foraging game. But the big question is, okay, I mean, people are very good at this in the wild, animals are very good at this in the wild, but does that happen in the lab? And it seems like that is true. Like for example, in this study, these are two monkeys. So we train monkeys to play this game. So two monkeys that played the kind of game that I showed you. So here it shows you travel time, and I'll tell you what this is. This is essentially the distance between trees. So let's say the second tree is like very far away, then you might as well stay in the tree that you're in for a longer period of time, right? Because you're going to spend a lot of energy traveling. Then you might get a few more poorer fruits before you jump off to the other tree. So this essentially shows that the travel time between trees increases, you end up staying for longer and longer. So that's why the slope is tilted that way. But the light blue line shows you what is the optimal time to stay, and the green line tells you what is actually, so the green line is the optimal, and the light blue shows you where the animal decided to live. And you can see that it's very, very closely matched to the optimal. So that means even in a virtual game, the monkey was getting juice for picking fruit, and it was still able to solve this problem quite well. And in fact, this is true even for human subjects. So this is data that we collected from about 161 subjects. And you can see here that this dashed line here is the optimal time to leave a particular patch. And you can see on average that people are hovering around that optimal time. So you don't have to really give them much instruction, but they seem to be able to naturally calculate what is going on. But one thing you might notice here is that on average it's optimal, but why is there a lot of scatter, right? Like you see that some people are leaving late, some are leaving early. So that got us thinking in terms of maybe this is how the changes at the circuit level are manifesting in the behavior, and we need to get a handle over what is going on here. You might also, like in this sort of a game, you have to continuously click on this option or click on this option, so it takes a little time, just like you would put your hand out to get fruit. Some people are really fast and rapid, like they can actually like pluck very fast, and we've seen this around, right? When you go with a bunch of friends, we can see that some people are more faster than other people. So how quick you are also might impact how many fruits you get at the end of the day. So we have to sort of control for all of those things as well. So we did look at the time it takes to sort of respond in these conditions, and there was quite a bit of variability from 2.5 to about 3.5 seconds, right? Like that is, some people are very quick, some people are slower. So these are in seconds. It doesn't seem like a lot, but it still can impact all these things. And this is exactly what we found. That is that so that defines when they should leave the patch. And you do see that in the behavior as well. So people who are slower take longer to leave, and people who are faster leave sooner. And models that included response time were performing better. So this is still a sanity check in the sense we've not still looked at anxiety. We're only saying that there are differences in terms of how people respond, and that can also change what is the right thing to do. But now we're going to go and check that even despite factoring in all of this, are there changes that anxiety plays over? So for this, we decided to incorporate what is called a process model for decision making. So this, if this looks complicated, I can simplify this a lot. There's nothing really going on here except that if there are two options at every point in time, so you have to decide whether you have to stay in that particular tree or leave that particular tree. Right? So two options that you have, or say go back to the same restaurant tonight, or switch your restaurant, or do I continue to be friends with this person, or switch and go to the other person, something of that sort. So you're always thinking of a lot of decisions in life either as a stay leave decision, and this is one such as well. And you have two options. You have option 1 and option 2, and typically the evidence that you have for each of these options defines which option you would select. So for example, if you have a lot of evidence for the same restaurant, that is, food is good, taste is good, that's the kind of food that you like, then you will quickly make that decision, right? So you might start neutrally to both options, that is, you don't really have a preference for either one, but you quickly have a lot of evidence for option 1, and you make that decision. So this model sort of captures that time it takes to make that decision, given the evidence that you have for any of these particular options. If you have less evidence, then of course it takes you longer to decide. If these two options are almost equally good, so then there's less evidence favoring one over the other, then it takes you longer to make that decision. Sometimes you're in a hurry to make a decision, right? Because the auto will leave or something like that. So then you have to use lesser evidence to make that decision. So you're clapping it down in some sense. You don't have time that you would have otherwise. But essentially, this is the computational framework now that can be used to say, this is how quickly you make the decision based on how much evidence you have. You can turn this into a model that explains patch coding as well. So you have to decide to stay. You decide to stay because the reward that you're getting in the tree right now is much better than the average reward in the environment. So you're sort of pitching the currently available reward against the average reward available in the environment. And if it is very high, that is if this is currently the tree you're in, got lots of fruit, then there is very high evidence for you to stay in the particular path, and you're going to be making these decisions very quickly. But at some point, the boundaries converge because there is a sense of urgency to leave the tree, right? Like there is a sense of urgency to sort of be done with getting fruits there and leave the particular tree to go to the other. So essentially, you can use this framework, even though this is developed for general purpose decision making, to also understand what's happening in patch coding. So where am I going with all this? I'm taking all this, that is the way you make decisions, the time it takes for you to make decisions, and whether you're making things optimally or not, to now see whether that can tell us something about anxiety. So in general, here's what you would see. That is, this is like what I'm trying to say is that this is your motivation to stay. The motivation to stay is lower if there are less rewards, and this is what you see here as well. So as the as you the number of harvests in a patch, that is, if you get more fruit in the particular tree, then your motivation kind of goes down, right? Like that's really what this is showing against the other plots right now. Okay, so now all I've said so far is that you can use path foraging as a way of understanding what's going to happen in anxiety. And now path foraging decisions can be studied using a computational framework like this one. But now can we really understand what is going on in anxiety? So that's where we're coming to in the last step. So and we're trying to catch people at this level where they're still subclinically anxious. They just stay anxious because they worry a lot, but they're still not clinically diagnosed anxiety. Yeah. So we also did this. So just to contrast what is trait anxious with state anxiety. So state anxiety is momentary anxiety, like I'm anxious because I'm giving a talk, but after the talk I'm totally fine. But if you continue to be anxious throughout, then that is really what the problem is, right? Like we want to distinguish trait from state anxiety. One way to do that very effectively is using a task like this, where you can. Oh, I think I forgot to say something. Okay. Yeah. So you can, like for example, put someone's hand in like ice cold water. This is like a brutal torture, right? Like you feel your hand pain, but that can actually increase your anxiety levels a lot. Another thing that is a very potent way of increasing anxiety is what is called a clear social stress test. So essentially, you tell people that they're interviewing for their dream job or something like that, but they don't know who's judging them. So there are people sitting in front of them, protected by a mirror, so they can't see them, and they don't get feedback, and they're asked to like continue to explain why they should be selected. And this is actually like being evaluated by people is actually one of the most potent stressors possible. So you can actually like really double the stress levels that someone is in right now. That's why talk is stressful, right? Because you're in front of an audience talking to a whole group of people and fully vulnerable to being judged by them. So that's why it's very stressful, right? And we also did the same thing. So we called people, we put them through the very rigorous stress induction framework, and we asked whether increasing their stress and anxiety in the moment, what does that do, as opposed to their long-term baseline anxiety. Okay, so here's, I mean, it just shows you that you do see a strong increase in anxiety by making these manipulations. And that also changes the way they respond to the current reward. So that is, blue is the baseline. This is how motivated they are, how quickly they decide to stay in a particular path. But you can see that that clearly increases when you stress them out, right? So orange is stress in the moment. But if they have a long-standing baseline anxiety level, then this blue line drops down. So this is actually a marker for trait anxiety in terms of like long-standing baseline increase in levels of anxiety. Is shown as a reduction in motivation to engage in the path. So by using this sort of a framework and a causal manipulation, we could sort of tease apart what is momentary anxiety from what is long-standing trait anxiety. So state anxiety seems to be increasing the motivation to stay, whereas trait anxiety seems to have decreased your motivation to stay in a particular path. So this is really what is being summarized here as well, so that you could use these decisions along with these computational models to say and tease apart anxiety from these two different timeline perspectives. Okay, so I mean, I've built the framework. Now I'll tell you how we go into the brain or look at the signals that are associated with this. And I said earlier that there are certain regions in the brain that we are interested in because those are the circuits where these calculations for the game as well as your anxiety sort of impinges on. We used this framework where we were trying to measure EEG. So this is electroencephalography, which you may have already heard about. EEG caps have probably been to EEG clinics, and there are faculty in the department also using EEG devices. So you're probably very familiar with EEG, and you could use certain EEG signals. For example, in this case, we use what is called the ratio of the beta band, the theta to the beta band ratio, which has been a marker for how you are distracted in a certain situation or how focused you are in a certain situation, as a marker for what is happening in the pathology task. So that is, if your tendency to disengage is a lot higher, then you must see very high theta beta ratio, and this is really what sort of used in this condition. And we could see very clearly that trait anxiety was affecting behavior, like I showed you earlier. But now the question is whether all of that is mediated via this theta beta ratio. And in fact, we could go ahead and prove with a fourth study that by using theta beta ratio as the mediator in this case, we could clearly show that they were disengaging much sooner than you would expect in regular healthy participants. So far what have I said so far, that basically you can use a task like a naturalistic origin task to elicit individual differences in behavior. You can then use computational modeling, kind of like the drift diffusion model, to get access to certain parameters which are not visible at the surface. At the surface you can only see people staying in a tree and leading a tree. But now you can start getting access to things like motivation, things like urgency, and you can factor all of that into your model. Right? And then you can manipulate the states that they are in by increasing stress or decreasing stress. And finally, by using all of this together, you can capture markers in their EEG that are reflective of how they disengage from a patch. So now I'm going to the last segment. So what can we do with all this? What is the application at the end of the day? So whatever I said so far, I've said that your state anxiety, your foraging decisions, and your physiological state, that is using all of this together, you're able to say that someone is state anxious or not, right? So, but can we turn that all into, turn that all around and say that if I give you these things, can you predict what trait anxiety, the value of trait anxiety is? Kind of like the thermometer idea that I was hinting at. So this was. I mean, of course, we need like very good EEG devices for this. And when we started off, we wanted also like devices that are easy to put on, because at the end of the day, you have to use this in the clinic, in outpatient settings, and it should be convenient enough for participants to wear this as well as play the game, and or maybe take it home and continue using this while they are under treatment. But of course, a lot of EEG devices are very bulky. They need an extensive setup time, very expensive, not very easy to use elsewhere. And so that's on one end. On the other side, the consumer grade devices that you have available, most of them are convenient, but at the same time, the quality of signals that you get is poor, or the reliability of data is not very high, and they also suffer from severe motion artifacts. So essentially, if you want to make this a very realistic scenario where you are collecting data as the person is moving around or playing a game or shaking their head or whatever, you still need a device that is wearable, convenient, but at the same time gives you very high data quality. So that's really where Fogware comes in. So this is a company that I co-founded when I was in Europe, and we essentially made a system that is clinical grade, can be used anywhere, anytime, and gives you a standard of care markers for all of these conditions. And currently, so although the first device was developed in the US, since I came back, we've actually gone in and made a completely indigenous version of this EEG device, which is now undergoing clinical trials with ICMR backing. So the company has grown a lot with a lot of scientific advisors and others. But essentially, what we can do today is using the sort of markers that we've developed, we can, along with an app that has the built-in algorithms to diagnose all these conditions, we can diagnose with a sensitivity of almost double what you can with surveys that are there right now, whether someone is state anxious or not. So that is where we are at the moment. I mean, of course, is this enough? I mean, this is definitely not enough. A lot of work has to go in terms of validating this in the clinic, which is something that we are starting to do. Working with clinicians to also use this as a support tool, because a lot of times during interviews or during diagnosis, your social stigma will kick in, and you might not say everything that you really want to say. But these games are things that you effortlessly play, and you can still get access to certain things without explicitly asking questions that make you uncomfortable. Right? So that's where the advantage is. Okay, so that's where I'll end this. I just wanted to thank all the funding agencies as well as the lab. But before I go, I just wanted to point out to the person, which is the PhD student in the lab, who's kind of helped with all of this work in the lab. And I wanted to also like broaden the framework of what goes on in the lab before I end the talk. So in the lab, I mean, this is the main thing that it's called the decision lab, and we are at IIT Kanpur, and we try to understand how we make decisions, and that's why it's called decision lab. And in real life situations, so we make games like the ones that I talked about. We also, I mean, we study this in humans. We also study this in non-human primates, so monkeys essentially. So we train monkeys also to play the game. And you might say, like, why should I work with monkeys? The reason why we should work with monkeys is that we are our closest cousins in some sense. The brain is remarkably similar, and you can also implant electrodes in these regions of interest to really understand what is going on in the brain, which is very hard to do in humans. Right? You can only do this in people admitted in clinics, but that is, you only get a subset of that. But in monkeys, you can potentially train them on all these tasks. I mean, they sometimes perform even better than us. And you can also have these implants that can go into the brain in those specific regions, and you can ask certain questions that you can never do in the brain. And for that, we need implants, right? Like, we need electrodes. These are the kind of electrodes that, for example, you might now have become popular based on what Elon Musk is doing at Neuralink. But we are making them completely in-house right now. So an indigenous line of electrodes that can be used for neural recording and reading from different brain regions are being made here as well. At the end of the day, we want to look at the brain states and stimulate those brain states with our electrodes and really ask how the brain circuits are facilitating the behavior that we are interested in the hope of finally having some data-driven insights for the underlying mental health condition. So that's the goal at the end of the day. So essentially, using various behaviors along with neural circuits to bear on the psychiatric condition of users. I just wanted to leave you with one slide because this is something that, so currently at IIT Kanpur, we have a whole lot of people across different departments like biological sciences, where I am, and there's cognitive science, and there's also electrical. So we have like a bunch of people across these departments that are that are working on very different aspects of neuroscience, including various different animal models from Drosophila to mosquitoes to mice to monkeys. And so on. So and also like very different lines of inquiry from olfaction to like reward-based processing to like computation and so on. So what we've done this time that's slightly different is that we wanted to actually have an open house on the 3rd of April for anyone who's interested in what they can potentially do at IIT, right, going forward in any capacity. It could be a short-term project, long-term project, PhD, and so on. So if you are interested, feel free to join, and with that I'll stop.
People that are pretty conscious in the past, one would think that if they have treatment diabetes, they're less likely to avoid internet movement because of stimulation.
Oh, so yeah, so I mean that's a very good question. So there are many different ways in which trait anxiety will manifest itself. Sometimes you might be afraid of uncertainty, and therefore you tend to stay where you are. But typically, what has been observed in trait anxiety is that, or anxiety in general, is that you don't have the, I mean, it's not like you lack the energy to explore. You're sort of worried about what is out there, so you want to sample everything and reduce your uncertainty, right? So you feel safer. So you are like jumping around to make sure that your world is as stable as you think it is in some sense. So that's why you have this increased tendency for exploration. In our task, it manifests as leaving sooner. But if you have like certain other tasks like where another very popular task is the bandit arm task. Like you have a 4-arm bandit or a iron bandit. Like these are basically machines that give you some reward, but each button gives you a different reward, and the reward distribution change over time. You tend to see people who are high anxious explore a lot more than who are low anxious. Yeah, but if you are thinking from the perspective of depression, like where you lack the motivation to engage or you lack the motivation to do much. I mean, you don't really care about rewards. Then why should you even do any of these things, right? Or the reward doesn't matter to you as much as it does to some other person. So in those cases, you do see reduced exploration, and you stick to things. But there, like the overall umbrella is reduced motivation rather than not wanting to explore for maybe 1 to 7 years.
Some of them may not be like the practice about training.
Right. Yeah.
Like
Right.
Yeah.
Yeah. Yeah. Yeah, for sure. I mean, that's a great question as well, because you are bringing people to the lab and you're making them play a game on the computer. Although today this is taken for granted, like that everybody has a computer or has some experience with computers. But what we have seen is that people who are like very avid gamers, like they game every day and they are very savvy with handling the keyboard, and they're always thinking about how to maximize the work in these conditions. It does definitely show. So there is going to be that level of noise in the data that is dependent on game practice and so on. But so they might, like let's say they might portray some kind of optimal planning, but they might also be anxious at the end of it. So there is going to be that sort of a little bit of that sort of noise in this for sure. But with large amount of data, the hope is that you are able to take out anything that is not correlated with the
You started your talk very nicely, saying that some of your signals would command you to run away. So do you think sort of combining more of this information, you were showing this device only with EEG, but our body movements, our heart rate, is there, you consider the integration of this information?
Yeah, so we did do a study. I mean, there is of course a lot of information. For example, the heart rate variability gives you a very strong signal for at least from the autonomic nervous system, which we wanted to also research. Also skin conduction. So I talked about sweat. So sweating is a very clear sympathetic response, very untainted by the parasympathetic response. So we have a study where we looked at skin conduction, heart rate variability, pupil dilation, again another marker that is also very nice signal for the sympathetic activation, and also E. So we've compared contrast with all of these measures. Heart rate variability seems to be so they can be contrasted in terms of how much sensitivity they add or activity, and also the latency. And when you do that, you do see that heart rate variability is very good. It's also like very quick, but EEG tends to be like the most informative. And you could do that with. I think we would want to do this in very natural conditions, but at the same time, the reason why we want controlled tasks is also because we want to employ specific techniques. So that's why combining, having these modalities, but also putting them in a certain framework gives us more significance. I think that's why we're progressing. Yeah. The central problem, I think it's not so basically these are soft sensors, and they don't move against the skin, and they kind of stick to the skin without using any adjustment. So that's one major thing, because any movement against the skin and any gaps in the contact is really where the impedance goes up and it starts picking up a lot of things. So these are dry electrodes. Yeah. So these are dry electrodes. They're soft and dry, and then yeah. These are they have metal nano wires inside the so that's one advantage, and so that minimizes noise. and noise also is picked up in the wires and also the design of the amplifier. So they were like, I mean, over a period of years, like we made lots of changes to it. That now you can actually put this on and like walk around and it's totally fine. Doesn't take anything. So I mean, for sure, for sure. I mean, those are actually stronger signals than what you get. Like time lock, event-related EEGs are like in microvolts, so I mean, very tiny in that sense. So if it works for that, I think it should work for us. And the amplifiers, I think the basic core chips that we're using are being used in ECGs anyway. So I think it should help us to.
Right. So what the steps that you were showing,
Mhm.
for anxiety that the problem is asking, people who do not know the play might get more anxious if you are asking them. But there are more anxious situations like, people get highly anxious when they have a test and then the next day or they perform something or something like that. So how having more tests that are really related to subtle anxiety other than just anxiety?
Yeah, so for example, the stress induction task that I was talking about, that essentially tries to tease apart these two conditions. So one is in the moment anxiety. So game is inducing anxiety, or the talk is inducing anxiety, or the test is inducing anxiety. But that might, I mean, that happens to most of us, and we need that response to actually cope adaptively to those conditions. But at the same time, you might have an underlying level of anxiety that is very long drawn chronic, which is what is debilitating. It's like all the time you're suspecting something will go wrong. Like that is the part that we want to do. So there is a lot of overlap in these two systems, but we still are able to computationally identify the differences between these two systems. So, like putting their hand in cold water or like making them speak or say why they're good, like those are trying to tap on that momentary anxiety in the most natural way possible, and trying to take that out and see what is underneath, which is the underlying space anxiety in those conditions.
And thank you very much. And one more question, like anxiety and depression literally have two opposite responses, right? But what does the physiology talk between anxiety and depression? And also, how is it, anatomically responding to these two how is these two distinct, totally opposite, but then still maintaining
Okay, so I might not be the most qualified to answer this, I'm not a psychiatrist or trained in medical practice. But to the extent that I've understood, I mean, I've been reading about all this for like maybe 7 years. But to the extent that I understand that, I mean, first of all, the way DSM-5, like that's the manual that we're using right now. And in general, I mean, DSM-5 applies to the whole of mental health. And it is still extremely symptomatic based classification of diagnosis, right? That is, we are looking at a set of symptoms and we're saying this is what it needs to be different. If you're feeling very hopeless, if you're feeling, if you're not motivated by reward, yeah, it's very low mood, persistent low mood for a period of time, and then some ancillary symptoms, then they call that as depression. For anxiety, it is what I said, like worrying and other things. Right? So it looks like, oh, we can categorize people as, some are anxious, some are depressed. But then when you go to the real world, it becomes really messy because you see a lot of comorbid anxiety and depression, which happens to a large number of people. And even more absurd is, I mean, it's not absurd when you think it's all based on symptoms, is that you also see these symptoms in other conditions. Like there are people with schizophrenia diagnosis, but they are also anhedonic, like in the sense they don't respond to rewards and so on. Like, so that's available. So I think since the last maybe like 2010 onward, there's been a huge drive in the mental health space to come out of the symptom-based understanding, because there is label that is convenient, it is helping in some way, that's why it's prevalent. But if we really have to go beyond this, the other reason is, comorbidities aside, treatments are also lacking efficacy, right? Like people respond, usually you give the same kind of drugs, SSRIs work, anxiety depression doesn't work, you change, try a different SSRI. But there's still a large number of people that don't respond to any of these drugs. And So all of this is kind of taking the question as to how can we make progress? Like where do we go next? So one approach has been this research domain criteria. So people are starting to look at basic symptoms. Like let's say you take one symptom and you look at the circuit underlying that symptom and see whether you can do something about that, like modify it or change it, increase or decrease the symptom in some way, so that we have traction over what is happening. And that symptom might be there across different disease conditions, but it doesn't matter as long as we have some traction over it. So that is the somewhat newer approach, still not very well accepted in the community, but people are starting to go towards that circuit level understanding of these symptoms. And this is one step in that direction. So we are just looking at this tendency to explode or tendency to disengage as a marker for anxiety. But this might as well also be there in schizophrenia. But that's why it stands diagnostic in that sense. But it tells us more about how the brain functions in a certain condition, more so than it tells us about anxiety. So at the end of the day, maybe it is some three different circuits that we have to deal with, and not something that is called anxiety on top. So there's so much heterogeneity that those classifications start to lose their significance.
Foraging of food versus foraging of knowledge.
Very good question. So, if you spoke to my postdoc advisor, he would say life is a foraging game. And I've started to sort of subscribe to that idea. The reason is that even though today we don't actively engage in like foraging food, we do still, like we do restaurant hunting or whatever, but it still happens in many different ways. Like people have done these studies where they say you're reporting words, like you just have to like keep saying like so they'll give you like some pointer and you start saying words. The way you you say like chair, then table, you'll have a cluster of words that are very nearby, and then at some point you will jump. Then you start talking about buildings and other things, and then you'll jump. So, but at the outset, if you like, look at it top down, it looks very, very much like foraging. Like you're looking for nearby words. When you run out of like those words, you make a jump, go to the other place. So that seems like foraging. Information search, like if people have done this again, like you've gone and looked at your search history in Google, or how you scan the newspaper. You might typically see a headline, you read something associated with it, and then you jump at when the value goes down, which is something like that. So people have tried to, basically the idea is that some of these circuits develop to help you find food, find mates, help you survive in those conditions. But now they're being co-opted for other behaviors that are helping us today. But the underlying circuits don't change so quickly, so it's still there, helping you in certain ways. Can be different, yeah.
As we conclude this informative session, we extend our heartfelt thanks to Dr. Arjun Ramakrishnan for his enlightening talk on neuroengineering for mental health, understanding suboptimal decision-making in anxious individuals. Once again, thank you, sir, for sharing your expertise with us. As a token of our appreciation, we would now like to felicitate our esteemed speaker, Dr. Arjun Ramakrishnan. I kindly invite Dr. Kavita ma'am to present a memento to sir. Thank you, ma'am, for doing the honors. I kindly request all the dignitaries to come up to the stage for a group photo. I kindly request all the dignitaries to come up to the stage for a group photo. For the next session, it is our pleasure to welcome Mr. S. Jayakumar, the CEO and founder of Comtech Scientific Instruments, Bangalore. After a master's in applied physics, he moved on to E.G. and G. Princeton Applied Research at New Jersey, USA, where he underwent extensive training in optical spectroscopy instrumentation, electrochemical and signal recovery instrumentation. He was also extensively trained in human and animal physiology instrumentation at ADI Instruments, Sydney, Australia. He was involved in the design and development of miniature fiber optic spectroscopy systems and is closely associated with Ocean Optics included Florida, USA, and miniature Raman spectroscopy systems with Wasatch Photonics, USA. Presently, he is working on AOTF-based and snapshot-based hyperspectral imaging systems from Qbert, Germany. He is the director of the Application Lab on Optical Spectroscopy at Comtech, Bangalore. Comtech Scientific Instruments has also been a proud sponsor of the ICBSII Conference 2025. Please join me in welcoming Mr. Jayakumar onto the stage. Welcome, sir.
Thank you, Aruna. So, good afternoon, all of you. Yeah. So, I'm going to give you a brief presentation on the different optical spectroscopy techniques that could be used for biomedical applications. So, to introduce, I think she's introduced me well. So, we have an applications lab purely for optical spectroscopy techniques, which include right from UV to almost far IR. It covers the entire electromagnetic spectrum. We have been working on almost all this kind of equipments. So to start with, I think you must have seen this slide almost in most of the optical spectroscopy presentations. So this is just to define the wavelength, the frequency region where we work when we call optical spectroscopy. So we work from the deep UV region right up to far IR region, which covers the electromagnetic spectrum in the ultraviolet, visible, and infrared region. So some of the techniques I will be focusing on are the Raman spectroscopy, Raman imaging, near-infrared spectroscopy, the transmission, absorption, diffuse reflectance spectroscopy, and specular reflectance, and also on fluorescence, luminescence, and lit. So to give you a brief idea of the working of spectrometer, I have just given a picture of a miniature fiber optic spectrometer, which we have one of its kind in our lab. See this, basically you have at the entrance, you have a slit over here, so where the light comes in, white light comes in. Then you have the first reflector, so which goes to a diffraction grating, and followed by a second reflector, which is the the collimating reflector, and which collimates onto the CCD array. Okay? Yeah. So let me start with Raman spectroscopy. I'm sure most of you would be knowing of Sir C.V. Raman, one of the greatest scientists of our 20th century. So he was a Nobel laureate and who invented the Raman effect. I think there's some problem. Okay. So Sir C.V. Raman is one of the most well-known Nobel laureates of the previous century, who hails from India, who discovered the Raman effect, even before the advent of lasers. Okay. So I don't know if how many of you have had an opportunity to see his lab where he worked? You know, it's based at Indian Association of Cultivation of Science at Kolkata. So there is a room where he has used almost 1,000-watt, xenon light source coupled with a monochromator, almost the size of this room. Okay, to get such a high resolution, monochromatic light, coherent light, so near coherent light. So the Raman effect was discovered based on that, for which he got the Nobel. He was awarded as a Nobel laureate. So after several decades, a laser was invented, and which came very handy to again start putting Raman effect into practical use, right? So even initially the lasers were quite expensive. Subsequently we started having these solid state lasers, which were, you could see some of these lasers in your laser pointers. So these lasers basically brought down the size, the cost factor, and the applicability of the instrumentation. So Raman spectroscopy is one of its kind where almost 1 in a billion photon undergoes this effect. So this is because of the vibrational, vibration of electrons which are excited by a laser beam. When the laser beam strikes the material, the electrons in the outermost electronic shell, basically they undergo certain vibrations, so which produces this Raman effect, 1 in a million. So these have a specific signature which is produced, okay, a fingerprint which is produced, and Raman spectroscopy is a molecular technique which can analyze a complete molecule, a signature of a complete molecule. So this is extensively used in several applications, like for detection of cancers, in detection of pharma drugs, and also in detection of narcotics, in explosives and so on. They have several applications. A Raman spectrometer, how does it work basically? So it uses intense light from a laser to probe the chemical bonds in a substance, generating a spectrum that acts as a fingerprint to characterize or identify the substance. So what are the things it contains? Basically it contains a high intensity laser, a sample interface, and a spectrometer, okay, optical spectrometer. So these are some of the different Raman spectrometers. Basically, Raman spectrometers are available at different wavelengths, okay, of the laser. So basically, you have based on the laser line, you have the Stokes region and the anti-Stokes region on either side of the laser line. So these actually define on the kind of materials you use. Basically, if you are using biological materials, people tend to go for either in the near-infrared region, excitation in the near-infrared region. The reason being there has been a lot of interference due to Rayleigh interference and interference due to fluorescence. So we have, depending on the application, we have different types of Raman spectrometers which are available. Here is a representative Raman spectra of a male and a female molar tooth recorded from apex in 3,500 to 200 centimeter inverse range. So these are fingerprints, so you can easily make out, if you have a library. Basically we also offer you with libraries from Wiley publications which can actually identify the material and tell you what exactly is the material and what is the state of the material. Researchers from Purdue University in the US have created a new imaging technology based on Raman spectroscopy that reveals subtle changes in breast tissues, representing a potential tool to determine a woman's risk of developing breast cancer and to study ways of preventing the disease. I'm sure most of you would be knowing there's a lot of work going on, on cancer studies, and we have been associated with some of the major hospitals like Amrita, Cancer Hospital, and also with Indian Institute of Science, Professor Vasu's lab, and also in IIT Madras with Dr. Sujata's lab. So we have provided some of the instrumentation behind this. Yeah. The other, this is another optical spectroscopy technique which is called as the reflectance spectroscopy. Basically, all these techniques, the best part is these are non-contact and non-destructive techniques. So basically, the reflectance spectroscopy, you have a probe and you have visible light or visible and NIR beam which is focused onto the spot, and then the reflected beam is analyzed for the various the color in the visible region and also the various constituents in the near infrared region. So this is a specific setup for monitoring. So you have a spectrometer here, a light source, and this is a fiber optic probe which could be used for reflectance of tissues and also on skin and so on. So here is a spectrum of different lesion groups and the DR spectrum, that is diffuse reflectance spectrum. So this can be easily correlated for the intensity of the lesion. And here is another interesting application of optical reflectance to estimate the bilirubin concentration in infants, newborns. Okay. So this is absolutely a very safe technique, and it's a non-contact technique where you could just focus the light onto the feet of the infant, and you would be able to get the bilirubin spectrum, something like this. And this is of to determine the blood volume fraction in the neonatal tissue. And as I told you, infrared spectroscopic biomarkers of breast tumors, discovery of quantitative optical biomarkers unique to cancer has been developed, and so to say, we have been working with several startup companies who have actually been trying to develop, even in Bangalore, using near-infrared spectroscopy. There are a group of startup companies who are working for, estimation of biomarkers for diseases like Parkinson's, Alzheimer's, and different types of cancers. Because these, even before the advent of the disease, these chemicals starts getting produced in the body, so which could be easily analyzed using the near-infrared spectrometer. And the NIR spectrometer is the most safest part of the electromagnetic spectrum, unlike the X-ray, which can do a lot of harm to human tissues. And so this has been extensively used. In fact, now there is a company which has developed a non-invasive blood pressure measurement, sugar level measurement in blood using near-infrared spectroscopy, because we all know that we have the invasive methods where you just prick and then a drop of blood is taken and then it's analyzed. So this is being done purely using the near-infrared spectroscopy using reflectance. Yeah, and here are some of the reflectance spectra which is being shown with healthy and unhealthy tissues. Yeah, then these are some of the applications. It can be used for detection of tissue inflammation, differentiation of benign from cancerous tissues, and differentiation of malignant lesions in the mouth, monitoring oral ulcers, and gum health monitoring. Some of the biomedical applications of reflectance. And this is one of the fluorescence spectrometers which is indigenously developed at Comtech in Bangalore. So we have actually made it very portable, so which could be actually taken for, by a doctor, which could be carried, and which could be for clinical examination, it could be used. And we have already provided one of its kind to, for oral health hospital in Bangalore, where they are doing clinical trials, and we've been getting very good positive results. And so to say, we have sold the same fluorescence spectrometer to almost all the major universities and IITs. This product was developed during the COVID time, when we had a lot of time to develop a proper product of this kind. So this is a very handy and small portable unit. Yeah, this is one of the fluorescence emission spectrum in the enamel of healthy teeth and a teeth with plaque and teeth with caries. These tests were conducted at the Victoria Hospital in Bengaluru, where we have given it for clinical trials. Yeah, and even for non-invasive early detection of oral cancers using fluorescence visualization with optical instruments is possible using optical spectroscopy and imaging. And these are some of the applications of fluorescence: detections of tooth decays and cavities, then monitoring oral ulcers, identification of oral lesions, identification of bacterial infections. And coming to the next optical spectroscopic technique, this is laser-induced breakdown spectroscopy. So this is relatively a very new technology which came in about a couple of decades, or less than 2 decades back, and which is commercialized about less than a decade. So now you see this is an alternate for equipments like optical emission spectroscopy and inductively coupled plasma and so on. So these are highly precise instruments, and this can do an atomic level investigation, and it covers almost all the elements in the periodic table can be analyzed. Basically, how it works is you see that you ablate a material with laser, so there is a microplasma which is created, and this plasma is analyzed using an optical spectrometer. Okay? So the best part is it looks very simple, but then when you're really analyzing, you find that there's a lot of interference in the main laser line, so you need a lot of other filters to remove the laser line, and also to use a pulsed light source to wait till the pulse of the laser dies down, and then you start measuring the the plasma. So these are some of the elements which could be analyzed using the lips. So almost you see that it's almost all the elements in the periodic table is covered. So the green ones you can analyze to a accuracy of 1 to 30 parts per million, and the yellow ones you can analyze from 30 to 100 parts per million, and the red ones you can analyze about greater than 100 ppm part per million. So getting the results, so this is actually using one of our lips spectrometers and imaging. So you can see that it is of basically it is a picture of the tooth. So the chemical changes have been identified. So you can get basically imaging as well as the spectroscopy and a pseudo coloring of the image based on the spectroscopic information. So that gives you basically what are the elements present. So you can see distribution of phosphorus in human tooth. Okay, cut human tooth. And in hard tissues and in most tooth you can see the level of calcium, magnesium and phosphorus and carbon and so on. These are all being taken with lips. Now coming to application of lips, of course it has huge applications in the biomedical field like organic tissues, hard tissues, and also it has applications in plastics and metals, and also in material investigation and in life sciences. Now coming to OCT, is optical coherent tomography. So basically, this is again a non-destructive three-dimensional imaging technique which is mainly used in ophthalmology, and now it is gaining great access into material characterization, into industrial applications besides ophthalmology. So it is an optical analog of ultrasound, something like an ultrasound. So where you have multiple beams which are focused on, and you get the complete image, a three-dimensional image. Same thing is done using optical beams here. Okay. So you can basically get a non-contact, non-invasive image of samples. So which gives you a complete, for example, you can find the depth close to about 1 micron. Depth can be distinguished in during optical eye measurements. So these are some of the high resolution imaging OCT spectrometers, which is extensively used in the fields of ophthalmology, dermatology, cardiology, neuroscience, and gastroenterology. Basically, it's wherever you use ultrasound, it's also used. OCT is used. So these are the choice of wavelengths. So we have wavelengths operating right from 400 nanometers, goes all the way up to 1600. That is to the near infrared region. And these are some of the applications in biomedicine for caries diagnosis, erosive tooth wear, caries therapy, composite restorations of OCT, and also in ophthalmology, cardiology, dermatology, and neurology. Thank you. Any questions? Basically this is used, the inside is a Michelson interferometer which is used. So depending upon the time lag between the different light beams which reach, so basically the three-dimensional depth is got in the near infrared region. It's a good question, because in the visible region, visible light cannot penetrate the human body, but NIR beams can penetrate the human body. That's why you have OCTs ranging up to 1600 nanometers. So there you will be able to do NIR imaging. Yeah. Yeah, it's kind of reflectance, but then you have multiple beams, and it is basically the lag. In a Michelson interferometer, you have two beams which run perpendicularly. So the difference in the time of arrival of the two beams estimates what is the depth. Yeah, based on that it is done. Yeah, please.
Well, it's not such a question, but there are two applications that I thought existed. The first one is, of course, you mentioned stimulation, right?
Absolutely.
But looking into let's start, what is the microbial mixture that are normally in infections, right?
Absolutely.
Another one is like, as you were mentioning, Dr. Patil, since you have one beam,
Yes.
if you have
Multiple beams.
exactly, you can like make three beams.
Yes, exactly, yes, yeah. Absolutely, yeah. In fact, even this microbial infections, there is also huge applications in Raman spectroscopy. Even Raman gives a wealth of information on that. So even Raman is used extensively in in estimation of microbial infections, wound healing, and so on. So that's also another complementary technique which is used extensively. Any other questions? Thank you.
Thank Thank you, sir, for sharing your valuable insights on optical spectroscopy techniques. It was a very informative session. I kindly invite Dr. David Pello to felicitate Mr. Jayakumar. Thank you, sir, for doing the honors. Now we'll disperse for lunch. The next session. Now we'll disperse for lunch. The next session will begin at 1:30. Please assemble at the hall by 1:15.